Good morning and hello everyone, and welcome to our workshop on map-based localization for autonomous driving. This workshop is being held in conjunction with ECCV 2020 this year. It is my great pleasure to welcome every one of you on behalf of all the organizers. The organizers of this workshop are Daniel Kremers, who is heading the Computer Vision and Artificial Intelligence Lab at the Technical University of Munich, and he is also a co-founder and chief scientific officer of Artisans Corporation. Artisans Corporation is developing visual odometry and SLAM solutions for the industry, as well as Ray Wang and Nan Yang, who are PhD students in the same lab, as well as researchers at Artisans. Also, Niclas Zeller, who is a research lead at Artisans. My name is Patrick Wenzel, and I'm a PhD student at the same lab and a researcher at Artisans. Just a short information on the event today. So we will have this live stream on Zoom. So I hope everyone found the link and everyone can follow. The procedure is as follows. We will have pre-recorded talks, and we encourage all the attendees to ask questions during the Zoom sessions. We will have Q&A after the talks, which should be live from the speakers. And we do plan to stream this event to YouTube after ECCV is finished. The detailed schedule can also be found at our webpage. The workshop overview. So this is the first edition of the workshop we are organizing at ECCV 2020. And the idea of the workshop is that we are mainly focusing on the topic of map-based localization for autonomous driving, because we believe this is a quite important topic to accelerate research in this area. The topics of our workshop are mainly centered about visual indirect and direct SLAM approaches, robust visual localization algorithms for changing conditions, which include weather changes, day and night changes, lighting changes, and so on. We also focus on self-supervised, semi-supervised learning, domain adaptation approaches, and of course, mapping and localization. The workshop overview will be as follows. During the day, we will feature 5 invited keynote talks. We will have 2 talks about challenge winner and the runner-up of our relocalization challenge. We would have 1 tech talk, and we have 1 peer-reviewed workshop paper talk. As I mentioned earlier, we have 5 invited keynote speakers. Our first speaker would be Dengxin from ETH Zurich, followed by Andreas Geiger, who is affiliated with the University of Tübingen and the MPI for Intelligent Systems, followed by Stefan Leutenegger, who is affiliated with the Imperial College London, and Raquel Urtasun, who is chief scientist at Uber ATG and also professor at University of Toronto. And our workshop will be concluded in the evening by a talk from Cyril Stachnis, who is a full professor at University of Bonn. So the workshop will be split in 2 parts. So we have the morning session, which is currently being held, which is from 8 a.m. till 11 a.m. UTC +1 time. So right now we will have the introduction to the workshop, and at 8:10 we will have our first invited talk from Dengxin, followed by a Q&A. And at 8:50 we will have an invited tech talk from one of the organizers, Niclas Zeller, followed by at 9:30 a.m. a contributed paper talk with the paper title Geographically Local Representation Learning with a Spatial Prior for Visual Localization. The morning session will be concluded from a talk from Andreas Geiger at 9:50. We will have a break, and we will continue in the afternoon at 4 p.m. again UTC +1 time, where we start again with a short introduction to the workshop, followed by an invited talk from Stefan Leutenegger at 4:10, which is followed from an invited talk from Raquel Urtasun at 4:50. Afterwards, we will have our relocalization challenge tasks, where we have the first talk at 5:30, which is the first place by Paul, Eduard, Saline, and others with the title Hierarchical Localization with H-lock and Superglue. At 5:50, the second place, Iroslav Melekov with the title Image Stylization for Robust Features. We will conclude our workshop today with an invited talk from Cyril Stachnis. Let me give a brief overview of our relocalization challenge, which we also host together with this workshop. So it is a visual relocalization challenge where we have built a reference map by visual inertial odometry fused with precise RTK GNSS measurements. We do provide reference and target pairs, which can be used for the relocalization. And we do capture the images with the stereo camera system. Particular for this challenge, we have been provided 5 different traversals of the same scenario. And the data for this challenge is part of a larger dataset, which will be published later this year at GCPR 2020. Stay tuned for the talk from Niclas Zeller. He will give a more depth overview of the data. Here in this slide, you can see the 3D reconstruction on the top of the slide from the loop we have been recorded in an industrial area around Munich. And on the bottom part of the slides, you can see 3 different images captured at different times of the day and at different months of the year, basically. So you can even see structural changes. So on the left, you have a small construction zones, you have drastic lighting and illumination changes. And of course, dynamic objects are also varying here. So how was the submission being handled? We provided 2 test sequences from different conditions with easy, moderate, and hard samples, where we provide reference and query frames, and the task was to estimate the relative 6 degree of freedom pose between reference and target frame. The ground truth test poses are withheld, and the evaluation was done by sending a text file to the organizers. And we had the requirement that the participants need to provide a paper also including archive, which needs to be available by the submission deadline. We would also like to thank our sponsors, which for the challenges, where we can have prize money for $1,000 for the first prize and $500 for the second prize. And we are happy to Artisans and CUDA to sponsor this. With this, I want to conclude the introduction, and I hope you will enjoy the event. And we will start with the first invited speaker in a second. It's my great pleasure to introduce Dengxin, who is our first speaker. He is a lecturer working with the Computer Vision Lab at ETH Zurich, and he is also leading the research group TRACE Zurich, working on autonomous driving with the R&D project TRACE, Toyota Research on Autonomous Cars in Europe. Dengxin obtained his PhD in 2016 also at ETH Zurich under the supervision of Professor Luc van Gool and Professor Gerhard Schmidt. During his PhD study, he was working on the project VAR City for city modeling based on camera data. And his current research interests include robust road scene understanding, learning driving models, and human vehicle communication, sensor fusion, and multitask learning. I'm very much looking forward to his talk.
Hello, everyone. My name is Dengxin from the Computer Vision Lab at ETH Zurich. So thank you very much for inviting me to give this talk at this excellent workshop. So in this talk, I'm going to present how to use semantic map for 4 different autonomous driving applications. So I'm going to present how to use semantic map for the end-to-end driving, and also how to use semantic map to improve object recognition in adverse lighting or adverse weather conditions. So later on, we will see how semantic maps can be used to predict the future action of other road agents. So in the end, I'm going to briefly present our work on how to use semantic map for ADAS system for motorbike over curves. So especially to avoid accidents there. So let's start with the first one, learning to drive. So in the literature, we know in order to learn how to drive, normally the input consists of the raw perception data like images. And then we have the localization state, for instance, like the position, the rotation of the vehicle. We have the ego vehicle state, for instance, the steering angle and also the speed, etc. So with this state, we can build a stack of modules like perception, prediction, motion planning, then to the control, the vehicle control. So more recently, we have another alternative approach which try to predict vehicle control directly from the raw data through a unified neural network. This is called end-to-end driving. So the end-to-end driving can be used as a standalone driving system. This can also be used as a sanity check for the conventional driving system. So here, if the prediction from both systems are consistent, we can consider this is a safer situation. If they are inconsistent, maybe we can call for a stop, or we hand this over to a human driver. So for this end-to-end driving, we have presented one work in ECCV 2018. So before this work, most people just work with a single front view camera only to predict the vehicle control. We find this is insufficient because you need surrounding view cameras, the rear view cameras in certain scenarios for safe driving. You also need a map or route planner to tell you where to drive if there are multiple choices in front of you. So for instance, here is an example. Both turning left and turning right actually are legitimate choices here. So we need a map to tell us where to drive. So for that purpose, we incorporate the TomTom map, TomTom route planner into our system. So with that, it's clear where to drive. But then we have a yield sign here. So in order to safely turn into this road, we need to see something larger than this limited field view from your front view camera. So for that purpose, we actually have we use the surrounding view cameras to cover the full 360-degree view around the vehicle. So such that in this case, we can see clearly about the traffic on this road in order to safely drive into that road. So with this setup, we collected 60 hours of driving data or 3,000 kilometers of road in Switzerland, which cover diverse road situation, also weather situation. We have 8 cameras here. We also incorporate the TomTom map, also the OpenStreetMap for the planned route. We also record the low-level CAN bus signal about how human drive, for instance, the speed and the steering control at each time point. So we also record the GPS IMU data, of course. So with all this data, we have developed a quite straightforward neural network to learn to predict the vehicle control. So we have the front view image sequence, the left view, rear view, and right view. We process them with the convolutional neural network, then integrate information with the LSTM over time. For the map, we can either render them into this real route map, like this one, or we can use the raw GPS trajectory of the planned route. So we extract the information here, we fuse this information, then we have a fully connected network to predict the steering angle and also the speed. So with that, I'd like to show a short video sequence of the result. So here we have a steering angle prediction. Here's about vehicle prediction code. The video seems that the video, okay, sorry that the video actually have some problem. Yeah, let's see whether the video, okay, so in this case, you see this is the right turn at this point. Then with the route planner, I think the video have an issue that we cannot see the video. So anyway, I just explain here. So here's the right turn. So with the route planner, actually our method actually figure out to reduce the speed with human driver together, reduce the speed, and also try to turn left from early point. But the method without the the map actually cannot do that, because driving forward here, driving forward is also an okay choice. Even turning left is also okay choice if there's no map, right? But the video here doesn't show that correctly. Okay, I think I will just skip the video here. All right, so if you look at the result, I mean, the evaluation, the numbers here, we find that the Vira route planner improves the steering and the speed prediction. So if you see here, without the route planner and with this TomTom route planner, the performance improved, the error actually reduced quite a lot. We also find that surrounding view cameras, they help in general, they help especially for low speed driving. So we analyze why surrounding view camera helps mostly for low speed driving. We find that the place we need surrounding view cameras are mostly in cities, in this intersection. For instance, here, especially about checking the oncoming traffic in other direction on different roads. So here we need surrounding view cameras. Of course, in these places, we normally drive at low speed. So here's a plot to compare front view system and the surrounding view system. We see for the low speed driving, the city driving, that the surrounding view system is consistently better than front view camera. However, for the high speed driving, for instance, in the mountain road or in highway, that the surrounding view camera doesn't help much there. Of course, that we maybe need to have a special network to extract the information such that the information density wouldn't be diluted by having more cameras here. So the surrounding view cameras still helpful here, we believe, but it's harder to extract that very little information out of the surrounding view camera for high-speed driving, let's say. Okay, so we find that the Vira route planner offer better performance gains than this raw GPS trajectory of future planned route. So the reason here is that the Vira route planner here, in this rendered map, we do see some high-level features, also the context information. For instance, about road layout, road attribute, about this exit, there's an intersection here. So these information are very useful for driving. We don't see this from a planned route, for instance, just a planned GPS trajectory. So this rendered map is designed to help human driver, but we also find it's very useful for neural network to learn useful information from this map. However, we find there's still some issues with this rendered map. So the full semantic knowledge is not available in this map because this is just distilled map by map engineer to help human driver. A lot of information, a lot of semantic attributes are not included in this map. Also, the accuracy is compromised when this is rendered into an image. So we need a semantic map with a full set of accurate map attributes that we can use for this end-to-end driving. So as a human driver, we know that we actually constantly use this mental semantic map. Like imagine like you driving this situation, your view is blocked by this truck here. If this is a situation somewhere close to your home, the situation would be very different from if you are in a new city where you don't know the road. For instance, if it's somewhere close to your home that you probably know, okay, in your mental map, maybe there's a crossing line, the pedestrian crossing line behind this. And then when you try to go over this truck that you have to, you actually will be very careful about pedestrian detection, right? But if it's in a new city, maybe the risk will be higher. And then we would like to use this idea, actually apply this idea to autonomous driving system by using the semantic map. So if the semantic map tells you there's a pedestrian crossing line like 10 meters ahead behind this truck, then we actually have to be more careful about pedestrian detection by maybe promoting or have a attention map for pedestrian, a higher attention map for pedestrian. So in order to augment our previous data set, we actually query these semantic features from the here map technology. We first localize our vehicle into the here map road map, then we query a rich set of semantic features. For instance, the distance to traffic light, the yield sign, the distance to pedestrian crossing, the speed limit, road curvature, turn numbers, also the geometry at intersection, etc., etc. So with these features that we can learn better neural network. So this is a method we have just presented before with the visual route planner. So now we have these semantic features here. We could just simply use a LED fusion with what we had before. LED fusion fuse them, then predict the control command of the vehicle. However, we find this simple system actually cannot give enough room to learn rich interaction between these semantic features in the map and also the semantic object from the street view. So instead, we learn this attention module. So we have this semantic feature from the map, then we have semantic segmentation from the street for the street view image. We have the segmentation confidence map for each of the class. Then we have to learn attention, this conditional attention map of this segmentation map to promote certain object classes and to suppress some irrelevant classes. For instance, the example we have used for crossing line, if the map tells you there's a pedestrian crossing line, we have to be more careful about pedestrian detection. If the map tells you there's a traffic light, so we have to be more sensitive about detecting traffic light, right? So this attention map, how to promote and then which map to promote and promote how much is learned automatically by the system. So once we learn this, we can actually feed this into the following standard component like say convolutional neural network, ASTM, and fully connected network to predict the speed and the steering angle control. All right, so with this new network architecture, we find that this attention model improves the steering and speed prediction significantly compared to this visual route planner we have used before. For instance, here you see that the error is reduced significantly. We also find that, I mean, in order to give like ablation study, whether this improvement is due to using semantic segmentation or is due to, I mean, having this attention on top of semantic segmentation and semantic maps. So we actually compare our method also to a method, end-to-end driving method, which uses semantic segmentation results. We find that our attention model also is significantly better than this like end-to-end driving system, which use semantic segmentation results. So this actually tells us that this attention map really allows for the rich interaction between the semantic features of the map and also the semantic object in the street view. Okay, so now let's move to our second topic about how to use semantic map for domain adaptation to have robust object recognition in adverse lighting conditions. So I think these days we have seen a lot of the demos about autonomous driving. However, most of them are done in a quite optimistic situation where we have good light and we have good weather condition. I mean, in reality, we have, this is a more realistic situation. We have different situations like fog, rain, snow, nighttime, etc. So we have to handle like all these situations. So this is the work we have done in ECCV last year. We also extended to a journal submission for nighttime object recognition. So the idea is to transfer the knowledge, the daytime model to nighttime. So we actually presented 3 ideas in this paper. So the first idea is instead of run this domain adaptation directly from daytime to nighttime, we actually collected and present a sequence of subdomains, intermediate domains in between. So we know from daytime to nighttime, there's a smooth transition over multiple twilight stage. Over here, we still have a good amount of light, right? So such that we can train a model here, which works quite well here still. Then we can retrain them with the generated pseudo labels. Then we can actually move forward more step, generate the pseudo labels, retrain the system. So this self-training can works quite well over this trajectory. So the second idea, we use this standard image translation algorithm to convert the standard daytime image such as cityscape to twilight style to nighttime style, such that we can use the annotations from cityscape dataset. So one important note we find here is, in order to use this cycle GAN algorithm for this task, it's better to use a smaller version of full images and rather than the image crops. So the reason is that this nighttime characteristic of different regions need to be captured, in this image context, in the full image context. Okay, the third idea is more relevant to the topic of this workshop. We find that we can use a map guidance for this domain adaptation or knowledge transfer. So the idea is that, imagine for this road, you already have a map. In this map, you have stored, like for every point, you have stored a daytime image with a semantic segmentation result, For the nighttime driving, you have a nighttime driving sequence here. For every image, first of all, you can build up this image level correspondence. You find for every nighttime image, you find a corresponding daytime image. Then we try to build up a pixel-wise correspondence over these two domains, over these two views. So we first use a feature matching algorithm to compute the relative camera pose between these two images. For the daytime image, we can also get the depth, estimate the depth of this daytime image. With the relative camera pose, with the depth, we can build up a pixel-wise correspondence. So this pixel-wise correspondence is especially useful to transfer the semantic knowledge from daytime to nighttime for static object. So in the paper, we carefully distinguish like the moving object and static object, such that we trust more on this image if the pixel is on a static object. We trust more on this image, nighttime image, if the pixel is on a moving object. So with these three, by putting these three ideas together, we find that our method actually outperform all other state-of-art domain adaptation methods quite a lot. So here we also compare to the baseline, which is the same neural network, but trained on daytime image. We find that we can also improve performance significantly without using any extra human annotation. So the dataset and the model of this method are made available. We also evaluate our method on other datasets, for instance, different datasets on nighttime driving. Here's the Berkeley BDD 100K nighttime image. We find the same conclusion. Okay, here's some visual results. Here's this, the left side is the nighttime image we have collected. And this is the annotation we created. In order to create this accurate annotation, we again need to use the map, like the reference daytime image in the map, in order to create more accurate annotations. Then when we compare to these two state-of-art domain adaptation method, we find that our method can give better result here. We also evaluate on the Berkeley, the BDD 100K night image. And although that the image, here there's a big domain gap between our training set to this evaluation set. However, we find that our method can do a quite good job here. And it also performs better than the competing method. We just mentioned how to use this map guidance to improve the training process. During training time, you have the daytime reference image and semantic segmentation result in the map, but we can also use this during test time, right? Imagine you have a car, you drive at test time at night, but if you have a map which has a corresponding daytime and the semantic segmentation result there, we can also use them to improve the semantic segmentation for your nighttime image during test time. So we evaluate for two methods. One is our method, another is alternative, like existing domain adaptation method. We find by using map guidance during test time, we can improve the performance consistently which is also reflected by this visual example. All right, so now let's talk about this, how to use the semantic maps to improve the future action prediction for the traffic agent. I mean, here I mentioned many times semantic map, and each time the semantic have a different, let's say, different forms of semantic segmentation map. They are not exactly the same type of maps. The representation, the knowledge stored in this map are different. I mean, so depending on the application, but we anyway call them, I mean, overall as semantic map. Okay, so for this task, we would like to predict, I mean, for every other traffic agent to predict their future action sequence over a few seconds. For instance, for the 1 second, you have maybe have the possibility to turning left or turning right. So what is the possibility in 2 seconds? I mean, this prediction needs to be in a probabilistic manner such that we can fuse this easily with downstream algorithm. So the prediction has to be human interpretable. We find this action sequence is more interpretable than the future trajectory prediction. And because this is a novel task, we have to generate a large data set to learn this. So we use the raw vehicle driving trajectory together with accurate HD map, semantic map to generate the data set. So I will present this in a second. So for the evaluation, as I said, compared to the existing trajectory prediction, we believe that this future action prediction is actually easier for human to understand. Also, it's easier to expose these corner cases. So for this, in order to generate this data set, we actually generate this data set from a no annotated trajectory data and HD maps. So this HD map consists of the road segment, and the road segment is indicated by the center lines, very accurate center lines. This map can be annotated, I mean, it can also be acquired from industry like map provider. So we find annotating map is more efficient and scalable than annotating trajectories, right? So the maps that you can annotate once and everyone else can just use the map. Okay, so in order to use this, I mean, generate this map, so we formulate this map as a hidden Markov model here. So each node is actually a length segment here. So each node actually forms a hidden state. So a sample from a trajectory is treated as observation from a hidden Markov model. So we use a Viterbi algorithm for this decoding in order to get the most likely sequence of state given the model as observation. So the transition probability are selected to reflect human driving. So you can find more details about this algorithm to automatically build up a large data set about the action in our paper. So the input, again, the input is a high definition HD map. Also, we have a lot of raw driving trajectories within the map. So we use the map information like the road segments, the center line, and to segment the driving trajectory into a sequence of actions. So we have an algorithm to automatically do this. Then once we have this constructed data set, we can build up a neural network to predict the future action sequence. So we use this spatial network architecture, which consists of early and late fusion. We use 2D convolution to extract the spatial information. We use 3D convolution for temporal, to integrate temporal context. So we render all the input, including the context, the map, the target vehicle's position velocity, ego vehicle position velocity. We render them into an image representation, which consists of 50 by 50 meter size. Now here's our data set statistic. We actually constructed over 200,000 trajectories. Most of them, of course, are about cruise. Then we also have a lot of left turn, right turn, the left lane change, right lane change to the left lane, change to the right lane. So because there's no existing work for the exact same problem, so we repurpose this ArgoWorth future trajectory prediction work for in order to compare. So this work actually it find or it outperform many other network-based, neural network-based future trajectory prediction. So okay, we find that our method outperforms this competing method quite a lot. The improvement is especially clear for these more difficult like action classes. For instance, turning left, turning right, left line change, right line change. So if you look more carefully here, so we have this sequence like two actions. We have cruise, turning left, cruise, turning right. So this is quite challenging to predict, especially about turning left, turning right. You see that our method actually outperforms the competing method quite a lot. And also the same for cruise, like moving forward, then which is followed by left line change, driving forward like cruise, which is followed by like a line change to the right. So our method again outperforms this competing method quite a lot. So in the end, I'd like to present like our work about this motorbike ADAS system. So for this motorbike ADAS system, we have also use a semantic map to improve to predict a better moving trajectory, to give the suggestion to the motorbike. So we know that up to like 17% of the accident of motorbike actually happened on the curve. And the main reason is that the motorbike doesn't have a proper speed and a proper intra-line position. So in this work, we actually propose a new type of road curvature warning system by using the convolutional neural network to predict the intra-line position, to predict the roll angle of the motorbike. We also use a hair map and this semantic map to get the very accurate road geometry of the future path. By putting this together, we use an upgraded controller model to actually predict a more realistic trajectory. With this one, we can give the suggestion to the motorbike, to the motorcycle for better position and better speed to improve the safety overall. Okay, so this is the end of my talk. I hope that I have presented my talk actually can provide some complementary view to all the other invited talks. Especially, I think it's quite interesting to give the views beyond like a localization for maps. So thank you very much for your attention. So if you have a question, we can also talk at the workshop, or you can simply write me an email. Thank you. Bye.
Thanks to speaker. Unfortunately, Dengxin cannot be here today to answer questions. But as he already mentioned, if you have questions, feel free to reach out to him via email. Due to this, we would directly jump to our next speaker. It is my pleasure to introduce Niclas Zeller, who is a research lead at Artisense. He obtained his PhD in 2018 from the Technical University of Munich. And before joining Artisense, he was working as an ADAS perception developer at Visteon in Karlsruhe. And his research currently interests include SLAM and relocalization based on different visual sensors. I'm very much looking forward to his talk.
Hi everyone, my name is Niclas Zeller. I'm research lead at Artisense, and it is my pleasure to give today this talk about visual map-based localization. Today in my talk I'm going to present Artisense technologies which were developed on one side by our research team, shown here, as well as our Artisense engineering team. At the beginning of my talk I want to ask a question, which is, why do we actually need accurate ego motion estimation and localization? One problem which we want to solve by that is vehicle control. Here we have to understand the motion of our vehicle with as low latency as possible. On the other side, we want to perform navigation and path planning, so we want to understand how we can get from A to B, and therefore also need the understanding about our location in the world. But most important, I think, is to extract information from an HD map. By being able to localize ourselves, with centimeter accuracy in a map, we can extract information about lanes, traffic lights, and traffic signs from this pre-built map. So how can we realize this localization? Of course, there are different sensor modalities which we can use. On one side, we have global navigation satellite systems, GNSS systems, which allow us to localize ourselves up to centimeter accuracy anywhere in the world, as long as we have reception to our satellites. Furthermore, there are inertial measurement units, IMU, which give us motion measurements of our vehicle with very low latency. And we have LiDARs and cameras, which we can use to perform simultaneously localization and mapping to track the motion of our vehicle within the world. Now at RDSense, we are convinced that the central sensor for a robust and accurate localization system has to be the camera, and therefore are different reasons. One is that the camera is a very small and passive sensor, and therefore can basically equip quite easily in any vehicle. Since it's a passive technology, we don't have to expect interference of multiple sensors. Furthermore, cameras are much cheaper than, for instance, current LiDAR systems or high-grade INS systems. And as a third point, as of today, most of our modern vehicles are already equipped with cameras, so therefore we don't have to put additional sensors into our car to perform accurate localization and ego motion estimation. Now, the problem how we solve this is localization is by performing visual SLAM. So visual simultaneous localization and mapping. There have been developed basically two parallel paradigms for visual SLAM. One is the so-called indirect approach, where we take our sequence of input images and extract so-called feature points from those images. Later, we try to match those feature points, those key points, between subsequent images, and we try to optimize for a geometric reprojection error in the images. Here, the problem is that we only can use those points which are actually detectable by our key point detector, and we also rely on the accuracy of this detector. Direct approaches, in contrast, skip completely this feature extraction step and perform tracking directly on pixel intensities. In this way, we are able to use much more information from our image, and we are able to track those points, to optimize those points up to sub-pixel accuracy by optimizing a photometric error instead of a geometric reprojection error between those subsequent images. One algorithm which solves this direct SLAM problem is so-called direct sparse odometry, which you can see here. And as I said before, this approach is exactly doing what I mentioned. It is tracking a sparse set of image points by optimizing photometric errors in a sequence of keyframes. Here in a sequence of 8 keyframes, where we jointly optimize our relative pose between the images as well as the depth of each of these points. And by doing so, we are able to track a single camera quite accurately, as you can see here, where we go through where a sequence is recorded through a subway station, and we see that if we perform a loop, we have quite small error between beginning and the end of the sequence. Now, one problem which we have for those monocular approaches, that just from the extracted geometry we are not able to tell anything about the scale of our scene. And even more important, that we don't know the scale, we also have the problem that while tracking a camera, our scale will actually drift. So, which means that at the beginning of our sequence, we might have a different scale estimated than at the end or somewhere in between of our sequence. And therefore, we have to ask ourselves this question to use Visual SLAM for localization, how we actually can overcome the problem of scale ambiguity as well as the problem of scale drift. And to overcome this problem, we can, of course, use different sensors or use additional sensors. So what we can do, instead of using just a single monocular camera, we can set up a stereo system and use two cameras to observe the scale of our scene. Furthermore, we can use inertial measurement units, and here by measuring the motion, so by measuring linear acceleration and angular velocity, at some point we are able to observe the scale from the sequence which we record. In our RDSense products, which you can see here on the right, actually we fuse both of those technologies. So we develop a stereo inertial SLAM system which allows us to accurately track the sensor and track it also with the correct scale. Now in our research team, developed further methods to use deep learning to observe the scale of the scene. And the idea here is that we actually can train a network to predict from a single image a depth map which has the correct scale, and now integrate this depth map into a SLAM framework. And this is what you can see here in the right video. So by using those approaches, either using additional sensors or using deep learning, we are able to improve our SLAM system and are now able to accurately track our sensor with the correct scale. However, what we are still not able to do is to localize ourselves globally, or to localize ourselves in a certain map, which is in a certain reference frame. So the only thing which we can do is track our position and our pose with respect to a certain starting point. Now, to overcome this problem, so to also be able to estimate our global position, what we can do is GNSS fusion. So we can use an additional GNSS sensor and fuse the information of our direct stereo inertial SLAM system with GNSS. And we fuse it with a highly accurate RTK GNSS, which is actually using correction services to get global positions with up to centimeter accuracy. Now, as I said, from the GNSS we get centimeter global positioning, and furthermore, by using our SLAM system, we get also locally accurate 6 degrees of freedom poses. And this way we are also able to estimate our global position even if we go into GNSS denied environments. So as long as we have open sky conditions, we get the global position from our GNSS receiver, and at the point we enter a GNSS denied environment, like a tunnel for instance, we can further track our position in the global coordinate system with the drift of our SLAM system. And this is what you actually can see here in this video. So this is a video which we recorded beginning of this year at CES in Las Vegas, and actually what you can see here on the left is our map where we started recording in a parking garage, so on the top level of the parking garage where we actually had GNSS reception. Then we go into a GNSS denied environment and still are able to localize ourselves very accurately in the map. On the right side you see the 3D reconstruction from our SLAM system, and you basically don't see any jumps if you go from inside, so from GNSS denied environments to outside, where we have GNSS signal available, and so where we have global positioning. And if we now go back, enter the parking garage again, and go all the way up to the top of the parking garage, we can actually see that we close our loop. So if we come back to our starting position, we close our loop quite well with basically no drift. And this is all done by just integrating highly accurate GNSS into our SLAM system without doing any loop closure or so. Now the drawbacks, of course, of GNSS is that global positioning is only available in open sky conditions, which also means that, for instance, if there can be trees or buildings on the side of our road which actually disturb the GNSS signal and don't allow us to get centimeter accurate positioning. Furthermore, to obtain centimeter accuracy, we all the time need real-time correction data. So we need always a connection to a base station which is measuring and transmitting those correction data to us. And furthermore, if we have a complete indoor environment, so also for instance if we start in a parking garage, we are not able to do drift-free localization, and we are also not able to do global or reference coordinate based positioning. Now, our solution to that is to perform map-based localization. What do we understand by that? So what we want to do is estimate the 6 degrees of freedom pose of our sensor with respect to a pre-built map. And here this map basically can be anything from just a collection of landmarks, so for instance some poles, some traffic signs, some traffic lights, lane markings, to a set of 3D key points which we have extracted from our images, or it also can just be a set of pose-referenced images. So just a set of images, a set of keyframes for which we have quite accurate 6 degrees of freedom poses in our global coordinate system. However, still the question remains how we can integrate such map-based localization into a direct SLAM system. And this is exactly the problem with researchers at ArtiSense, Lucas, Patrick and Kadir was working on, is how to integrate real localization or map-based localization into a direct SLAM system. One of the core algorithms in direct SLAM is direct image alignment, which allows us to estimate the relative pose between two images. And in general, we want to estimate the relative pose between two consecutive images in a sequence, but if we want to perform relocalization, of course, we want to get the relative pose of a query image with respect to a reference image, as you can see here in the bottom. And how we estimate this relative pose is by basically taking one of the image, taking all the pixels for which we have depth information and warp them into the other image, and then perform a Gauss-Newton optimization to optimize the intensity error between those two images based on the relative pose between the two images. And as you can imagine, for the case here, where we have two images which are actually showing exactly the same scene, but were recorded during completely different conditions, one can imagine that this direct image alignment will fail when performed on those images. So what Lucas and Patrick proposed is actually to replace the images by learned feature maps and perform direct image alignment directly on those feature maps. And now, instead of optimizing the intensity error of the warp points, we now optimize the per pixel distance between our feature vectors for those warp points, and in that way get the best possible relative pose between the two frames. Now the question remains how we actually can train those feature maps. And on one side, what we do for training, we define a contrastive loss, how it's also done for different image descriptors, by taking ground truth correspondences. So here in green you can see some ground truth correspondences, and what we want to achieve that our descriptors are as similar as possible for those correct correspondences. And furthermore, we take some random wrong correspondences, and we want to achieve that our descriptors, which our network is predicting, are as dissimilar as possible for those wrong correspondences. And furthermore, since we perform Gauss-Newton optimization in the direct image alignment, our researchers proposed another new loss function, which is called the Gauss-Newton loss, and this loss function basically rewards the convergency of the Gauss-Newton algorithm to the correct solution. So basically, in each iteration, we want to get as close as possible to our optimal solution. And if we now look at this in an application, as you can see here, we are now able to relocalize an overcast query sequence, which you can see here in the image on the bottom left, in a map which was recorded during sunny conditions. If you look at the 3D reconstructions, there you can see in gray the reconstruction of our map, which is overlaid with the reconstruction of our query sequence. And if you look at the lane markings, for instance, they almost perfectly align between our reference map and our query sequence. And what is also nice, which you can see here on the right, there are in blue quite some reconstructions of cars which were not present in the map, but which can be localized quite accurately in this pre-built map. And what is also quite nice to see, if you now look at in the images in our query sequence, there is now a construction site in a location where before there was no construction site. And if you look into the 3D reconstruction, basically you can determine the distance between the building, which was visible in the map, and the construction site, which was visible in our query sequence. We furthermore evaluated the generalization capabilities of this network. As you can see here, we used the same trained network which was trained on overcast and sunny sequence, and we see that it generalizes quite well to snowy and sunny sequences and shows quite similar performance here. Now, the main problem to train such networks is that we need good training data, and currently, in our opinion, there is no proper data set to train those sequences. So what you have seen in the video before was a network which was trained on manually aligned sequences from the Oxford Robocar dataset, but we actually think that there is quite a demand for a new data set. So therefore, we had the motivation to develop and to record a new data set, since we actually saw this demand for training data for cross sequence training. Furthermore, we wanted to have a quite diverse data set which has accurate ground truth, such that we are able to benchmark visual inertial odometry in challenging conditions, as well as relocalization in those conditions. And the idea was to get accurately georeferenced sequences by using our sensor system, so by fusing visual inertial odometry with RTK GNSS. And furthermore, we want to get accurate point correspondences based on those highly accurate poses, as well as the depth estimations which we obtain from our template stereo in the SLAM system. And we used the following sensor setup to record this data set. We used our stereo inertial sensor, which has a baseline of 30 centimeters, and we mounted it together on a rigid roof rack together with a GNSS antenna and put all of that on our test vehicle. We recorded for now more than 300 kilometers of sequences in 9 different scenarios, which range from urban scenarios to countrysides, to highway scenarios, and also to indoor parking garages. And for each of the scenarios, we recorded multiple traversals at different weather conditions as well as at different seasons. Now in this video you can see the diversity of the data set, so basically 4 of the scenarios which we selected. And in this video you can see for one of the scenarios, so for one of the sequence which we recorded, the aligned recordings of different traversals. So we recorded the same sequence of at completely different conditions, and you see that the images are perfectly aligned. Now, instead of doing this online GNSS integration, how I showed it before, we want to get even better accuracy by doing a post-processing. Therefore, we first run our direct sparse stereo inertial odometry to get locally accurate 6 degrees of freedom poses as well as the scene structure. And this you can see here on the right for one of our sequences, but of course here we have drift in our sequence, so if we revisit the same place a second time, you see that the 3D reconstructions are not perfectly aligned. And therefore, on top of this, we perform post-graph optimization, where we then want to get global accuracy and we want to compensate for drift. And this we do by loop closure detection as well as RTK GNSS integration. And if you now look in the same locations again, so on the bottom right, for instance, where we had before a bus which was reconstructed twice and clearly not aligned, this bus is now in this sequence perfectly aligned. And the same we can also do if we go indoors, so if we go in GNSS denied environments. Here you see the trajectory before post-graph optimization, and you see that the GNSS positions shown in green are actually quite disturbed. But still, after doing the post-graph optimization, our trajectory is basically perfectly aligned, and we also see that also in vertical direction our poses are quite accurate. Now to further validate the accuracy of our poses and of our 3D points, we actually can visualize the correspondences between different sequences as it is shown here. So we can take one point and project it based on the global poses of the images from one image into the other image. And what we see here, that those points actually align quite well up to pixel accuracy between 2 images recorded at completely different conditions and during completely different times. And this we can not only do for 2 images, but also for the entire traversals which we have for the same scenario, and we can map one point from one image into all the other images. And even if we don't really have features in one of the images, as you can see here in the bottom right, in this night sequence, where some of the key points selected in the top left frame are actually not really visible, but still align quite well. Now this dataset will be published at GCPR this year. Furthermore, we plan to release our data later this year, so stay tuned on updates on our dataset. And with this, I would like to summarize my talk. We first started to talk about the importance of localization in autonomous driving, and I showed how we can actually solve the problem of local tracking by using visual SLAM. Furthermore, we can do highly accurate GNSS integration to be able to perform drift-free localization in open sky conditions. If you also want to perform in GNSS denied environments, we can develop relocalization technologies which solve this problem. However, for those technologies, there is a quite high demand on training data, which we try to serve with our new data set.
So thanks to speaker. Now we have time for questions. As a short reminder, just use the Q&A functionalities of Zoom or the chat to raise any questions you have. You can also raise these questions already during the talks. I can already start with one question to the speaker. So the question is on GNet. Is there any guarantee on that the learned feature maps can always be aligned?
So I would say the short question or the short answer for that question is no. What we kind of can say that in the pixel vicinity where our network was trained, we can be kind of sure that it will converge to the correct solution. One other problem which I would say can be is if we have structural changes in the scene. So what we can train the network on is basically to learn appearance changes, but of course we cannot learn structural changes. And therefore, what we apply there is basically using robust cost functions, which kind of detect those outliers and downweight those outliers to guarantee convergency of the Gauss-Newton algorithm as often as possible.
Yes, thanks for the answer. Another one would be, have you observed any failure case of stereo DSO, DVSO, or GNet? As you mentioned already in your talk, that robustness seems to be a main concern for vision-based approaches. Maybe you can comment on this.
Yes, so I would say for accurate localization, of course, robustness is one of the main concerns which we have, because of course we want to have a system which is working basically in any environment and at any time. Of course, one challenge for vision-based approaches is if you have moving objects, as well as for the relocalization approach if you have, for instance, structural changes. But as I said before, to account for that, what we can use, for instance, are robust cost functions. So in general, if you perform Gauss-Newton optimization, we use a robust Huber norm, which basically downweights those outliers. And the other thing which we can do, or which we do in our product basically, is fusing the visual system with an inertial measurement unit. So therefore we get quite accurate low latency motion measurements which we can integrate in our system. And maybe then also when the vision system fails, we still can rely on our IMU measurements. I hope that answers the question.
Yes, thanks a lot. We would have another question regarding the maps. So the maps, the question is, the maps you use for localization seems to be too big to scale to larger cities. Do you plan to also go to more abstract compressed map representations?
Yes. So if you want to build a map at city scale, of course, using an entire set of images, might be too big and therefore cannot really scale. So, but there are also for initialization, what you would do is perform image retrieval, where you can use quite compressed descriptors of the images. And also for the direct image alignment, of course, you can reduce the number of points which you are using, and you can sparsify the map. So in this way, we are able to some extent compress our map, but of course for the direct approaches, since you want to use quite a large number of points to get as high accuracy as possible, of course you always have to make this trade-off basically between size of the map and accuracy which you want to achieve in your relocalization pipeline.
Okay, thanks. There's another question. What kind of IMU hardware did you use for the dataset and for the experiments? Was it automotive grade?
Yes, for the dataset we use an automotive grade IMU, which is it's an IMU, automotive grade IMU. Unfortunately, currently I can't say the model which we are using.
Yeah, but I'm pretty sure you can forward the model to the respective question.
Yes, I will.
Are there any more questions? If not, I would also ask one. How do you see the importance of semantic maps, and how do you see the importance of the level of semantic detail you would need for representing such a map?
Yeah, so if you are interested in localization, so basically we are not too much interested in semantics. If we go down to tracking, basically, of course, if at one point you want to be able to transfer data maybe from one sensor to the other, then maybe it would help if you go to a semantic representation of your map, that you rather start to detect or to represent landmarks in your map which have a semantic meaning, rather than just using a selection of points or using using those feature maps which we currently use to generate our maps.
Thanks a lot for answering those questions. If there are no more questions, then we would continue with the schedule. So our next presenter would be Jimin Chai, who is a PhD student from TU Delft, and he will give a talk on his contributed paper. I will play back the video in a second.
Hi everyone, it's my great pleasure to present at this workshop. My name is Jimin Xia, and I'm a PhD student in the Intelligent Vehicles group at the Delft University of Technology. This is going to be a talk about the paper, Geographically Local Representation Learning with a Spatial Prior for Visual Localization, which is a collaboration between Delft University of Technology and TomTom. Localization is always an indispensable task in autonomous driving. Usually, the location is estimated using GPS or GNSS. Without any GNSS base station or RTK techniques, the positioning error can reach tens of meters. Nowadays, most of commodity vehicles equip cameras. Consequently, visual localization becomes an attractive research direction in robotics and autonomous driving. Visual localization techniques explicitly or implicitly match an input image to some sort of representations of map. Therefore, the availability of those maps directly influences the practical usefulness of those visual localization methods. Thanks to the large-scale geometric surveying, satellite images nowadays cover most parts of Earth's surface and are publicly available. One category in visual localization, namely cross-view image matching-based localization, becomes very promising. Essentially, the task is to match a ground-level query image to a georeferenced satellite patch. Once the matching is found, the vehicle location is a geolocation of the center pixel in this satellite patch. We use a baseline method to do this matching. For example, one gets similarity measurements between one query image and all satellite patches in our database. Then we use this information to generate the following location heat map. In the heat map, each dot represents a satellite patch location, and the darker color the higher the possibility that the query ground image located at that location. Globally, the ground truth location is indicated by this circle, and the baseline can find out the coarse location here. However, if we zoom in to the local area where the ground truth location is at the center of the circle, we find that the baseline is actually quite uncertain about the exact location along this road. By looking again at the heat map, we wonder that in real-world applications, the coarse location can be already acquired from sensors like GPS or GNSS. Most of locations outside this circle can be ignored anyway. Then we might need a locally more discriminative image representation for this local neighborhood. Let's first keep this question and take a look of how the baseline model is trained. During training, the pairs of satellite patch and the ground image are randomly selected from all the global map. Commonly, people use a triplet loss to minimize the difference between image descriptors of matched pairs in the representation space. In the meantime, maximize this difference between unmatched pairs. As shown here, one branch of a network maps the ground query image into a normalized image descriptor. Similarly, the satellite patches are also being mapped here by another branch of a network. All descriptors stay on this unit hypersphere, and the similarity measurement often is a L2 distance between image descriptors. The goal of the training then becomes minimize this distance and maximize this distance. Since the triplet loss treats every triplet the same, and all samples can locate it at a random location globally, therefore, the resulting model becomes discriminative globally. Let's get back to our question. Do we really want a globally discriminative model? Actually, all recent cross-view matching-based localization methods aim at the task of global localization, and overlook a coarse location prior can already be acquired from GNSS or GPS at the test time, especially for the use case of autonomous driving. Suppose we are here. With the help from GPS, we can easily filter out the false location here. In principle, we are more interested in where am I in a local area, so we are here or here. Without GNSS base station and RTK techniques, GNSS positioning error can reach tens of meters. Nevertheless, we can still use this coarse location prior already in the training phase to learn locally more discriminative image representations. As an example shown in this figure, if our task is to distinguish two nearby images, we might need to extract the exact location of those trees. However, this is different in case of global localization. In the global case, the discriminative feature might from the style or the type of the buildings. All in all, our goal is to take advantage of a coarse location prior and to train a model which is locally more discriminative. We will keep the baseline architecture the same and only change the loss and our training strategy. To do so, we propose to add a geodistance weighted term before the commonly used triplet loss. It considers two aspects. Given a location uncertainty R meters as a prior, as this dashed line shows, it gives zero weight to the triplets which have distance larger than the given prior distance R meters. On the other hand, suppose in one triplet, the positive sample is located here, and the negative sample is located here. Then this triplet should receive a very small weight on their loss, since we do not want to force the very nearby images which have similar image appearance to have very different image descriptors. Specifically, we use a Gaussian shape function to control the magnitude of weight. On the one hand, we have a sharp edge at the prior distance here, and all triplets which have distance larger than this prior should should not contribute to the loss. On the other hand, triplets with very small distance receive small weights. And this function gives a smooth transition from the very close by samples to the relatively far away samples. We found out that without weighting down the very nearby samples, the network focuses on the subtle differences between very close by images, and this leads to overfitting. In a practical aspect, if we randomly select samples in a database, as the baseline does, most of triplets will have distance larger than R and receive 0 weights and slow down the training. Therefore, besides the geo-distance weighted term, we also propose to use local mini-batches during training. Basically, we use geolocation information of each image pair and only select nearby pairs into one mini-batch to calculate the loss. As shown here, once we select a center image, we can use a predefined radius R to draw this circle. And we only select nearby pairs into one mini-batch and ignore pairs which are located outside this circle. Our first experiment is conducted on the CVST dataset, which is a cross-view image matching dataset with GPS footprints. Unlike the region-based data split in previous works in the cross-view matching, we always keep all satellite images and do region-based split of the ground images. The training, validation, and test set are shown in blue, green, and red in this figure. The intuition behind this split is that in real-world application, we often map the area already, and we are interested in how the method generalizes to the new measurements in this target area. In our case, the new measurements would be the new ground query images. Here is a sample pair from CVST dataset. Basically, it contains a ground level panoramic image and the corresponding satellite patch. Actually, the baseline method first warps the satellite patch using polar transformation to make it look more similar to the ground level panorama, and we will follow the same pre-processing. We train our model with 100-meter location prior, and the baseline is trained without this prior. Without any network architecture changes, our model improved the recall at 1 from 65% to 74%, given a 100-meter location prior in the test time. For completeness, we also provide the recall without location prior. Notice that the recall with infinite radius is not interesting for real-world applications when we already have a coarse location prior from GPS. In the location heat map, again, each dot represents a satellite patch location, and the ground truth location is at the center of the circle. As it shows, our model is more discriminative in the local neighborhood, but the baseline is quite uncertain about the exact location along this road. To check whether our model exploits local features, we also visualize the features which go into the final image descriptors. We found out that our model pays attention at the poles and the street lights. Such objects are repeated at many different places, but they are quite useful in distinguishing other images along this road. The baseline method, on the other hand, ignores those objects and pays more attention on the road structure, which is more useful in finding out the global location. Our second experiment is conducted on the Oxford robocall dataset. To enable cross-view matching, we connect satellite patches from Google Static Map API for the ground level front view images. Here are 4 sample pairs. The distance between the first 2 pairs is 5 meters, and the distance between the last 2 pairs is 20 meters. The Oxford robocall dataset targets at the illuminational and the seasonal changes in images from different traversers along the same route. We do not include the ground images with extreme changes in lighting conditions, such as day and night. But those ground images due from different times and days and slightly changed weather conditions. So the dynamic objects and the kinetic conditions can be different in those ground query images. Since this dataset is much denser than the CVST dataset, we can use a more realistic location prior here in training and testing, namely 15 meters. Similarly, because the dataset is very dense, we report recall at 5 meters instead of recall at 1. It means once the ground image is matched to any satellite images, within a circle at a ground truth location with 5 meter radius, we consider it's a correct match. Our model, again, is locally more discriminative. And again, the recall without location prior is just for completeness. Besides this, we also report the distance evaluation. The top 1 distance means the distance between the top 1 retrieved candidate and the ground truth location. And our model gets smaller error than the baseline in both mean and median top 1 distance. To provide more intuition about how the baseline and our model work on this dataset, we also visualize the location heat map on the full map, local map, and the regular grid of satellite images. In the local cases, the cross indicates the center of circle, which is also the ground truth location. Satellite images in the regular grid case are not necessarily located along the roads, but both models are only trained with images along the roads. So this case shows the generalization capability of both models to unseen satellite images in the target area. In the local regular grid, the ground truth location is not always on the grid point, and the distance between each grid point is 5 meters. In most of cases, the baseline model is quite discriminative globally, but has local uncertainty in around 20 meters by 20 meters area. For our model, although it has no global localization ability, it's more accurate in the local area. And of course, the global coarse location can be easily acquired from GPS, so we can already ignore all the false positives outside this circle. Here are our conclusions. While previous work only focused on learning geoglobal representations, we have shown that a geolocal representation can already be obtained with easy to implement adjustments to the commonly used triplet loss. And there is a clear quantitative and qualitative difference between the learned image representations that must distinguish between either only geographically nearby locations or that must also distinguish between geographically distant locations. In the future, we will investigate how this geolocal feature learning affects other learned map representations. Thank you so much for your attention, and here are the authors.
Yes, thanks, the speaker. We would have time for questions again. If there are no questions from the audience, I would start with one question. So your method seems to be depending on the area, the radius on the local patch. So do you have a feeling on what is a good choice of the area covered in the satellite image patches?
You mean the coverage of the satellite patches?
Yes, exactly.
Well, we use the satellite patch from Google Static Map API. Basically, they have a limit of the satellite patch coverage, the scale of the area. So, in principle, we think on basically like hundreds of meters is okay for this method, since the ground view image can look at around hundreds meters distance.
Okay, thanks a lot. I would have another question. How do you get the GPS uncertainty measures for your method?
Basically, we do not have a GPS uncertainty measure at different location, but we get the common GPS error from literature. Basically, without RTK techniques, the error can reach tens of meters. Then we use tens of meters or 100 meters as our location prior for training and testing.
Okay, thanks a lot for answering. So you said for Oxford Robot Car, you acquired satellite imagery from Google's Maps, if I'm correct. Yeah. Is there any automatic way of doing it? Like, would it be scalable to other data sets as well? Or is there any manual effort included to obtain those satellite imagery?
Basically, Google Static Map provides an API, and we use an automatic way to get the satellite patches. When we provide the GPS coordinates to the API, then we can download the satellite patches automatically.
Okay, thanks a lot for clarifying. Then I would like to thank the speaker again, and we would move on with the schedule. Our next speaker would be Andreas Geiger. So it's my pleasure to introduce Andreas Geiger, the full professor of computer science heading the Autonomous Vision Group. And his group is part of the University of Tübingen and the MPI for Intelligent Systems. He is mainly interested in 3D scene understanding, reconstruction, motion estimation, generative modeling, and sensory motor control in the context of autonomous systems. His goal is to make artificial intelligence systems such as self-driving cars or household robots more autonomous, efficient, robust, and safe. I'm very much looking forward to his talk.
Thank you very much for inviting me to this workshop, and welcome everyone to this virtual presentation on 3D controllable image synthesis. This is joint work with my postdoc Yi and my PhD students Katja, Lars, and Michael. As we all know, there's two dominating paradigms in simultaneous localization and mapping. On the one hand, there are indirect approaches that take a set of input images, extract and describe key points, and match them in order to minimize reprojection errors for tracking the agent or for inferring the 3D landmark locations and building the map. And on the other hand, there are direct approaches, which also take a set of input images, but directly try to minimize photometric reconstruction errors in order to track the agent or estimate maps in terms of per pixel depth estimates. One work that I particularly like is the work from Davison et al. At CVPR 2013, where instead of a point-based scene representation, they consider an object-level scene description, which is much more rich semantically and also allows for much higher compression rates, so potentially allows the model to scale to much larger scenes. Now, one important point I'd like to make here is that current SLAM systems are mostly discriminative. They are large, sophisticated pipelines, which are composed of different modules such as feature detection, robust matching, loop closure detection, and mapping that are either hand-engineered or learned, but learned individually. Now, the question I want to raise here is, well, can we also build a generative model for SLAM? There has been a huge success recently in building generative models for images. So would a generative model for SLAM be useful? A generative model for SLAM would learn the observation manifold. It wouldn't require any supervision or any annotations. For instance, in the SLAM++ system, they required all of the objects to be pre-scanned using Kinect Fusion, and they also required pre-trained object detectors, for instance. Such generative models would also capture the uncertainty in the data, which is certainly useful for all processing tasks where there's a lot of uncertainty, such as in computer vision, and which also allows for making predictions and, for instance, for completing missing parts in the scene. But the big question, of course, is how can we solve this complicated, this challenging problem? And in particular, how can we disentangle the underlying 3D factors? And in this work, which you call 3D controllable image synthesis, we want to do first small baby steps towards this grand goal of computer vision. So in a simplified, from a simplified viewpoint, the goal of this work is to generate an image given a scene description that includes a pose and the appearance and the camera viewpoint of the scene, which can be used directly for simulation and training downstream tasks, for instance, or for verification of intelligent systems, such as safety critical systems like self-driving cars. However, of course, in terms of fidelity, we are still very far from scenes of that level of complexity. And these models could also be used in the Bayesian setting for estimating the latent properties given an image, such as for doing pose estimation or localization. So in brief, the goal of 3D controllable image synthesis, this is how we define the problem, is to learn a generative image model that can generate a scene composed of multiple objects, where the underlying 3D factors are controllable, where we have full control over the object shape, over the object pose, over the object appearance, and over the camera viewpoint, for instance. And where we learn all of this from 2D observations alone. We don't need, for instance, the pose of the input images, which is often not available. And we have also no other supervision, like semantic segmentation or depth maps or pose information. How do generative models look like today? So the simplest generative model is a traditional rendering pipeline, where there's an artist that makes a 3D model of the scene, and that is then rendered using a physically based rendering algorithm. By design, in this pipeline, the 3D factors can be controlled because they have all been manually created and arranged. However, 3D content creation is of course very expensive, and this is not scalable. And furthermore, creating photorealistic content is still an unsolved problem. So ideally, we'd like to learn this process, this entire process, from images. Recently, there has been a great success in photorealistic high-resolution image synthesis using generative adversarial networks, which learn from to generate from a latent code that's sampled from a Gaussian distribution, a image like the one we see here on the right, using a set of 2D convolutions. The advantage of this model is that this allows for unsupervised learning from 2D images where there is no artist required for the generation process. But the disadvantage is, while some of the factors can actually be disentangled to some degree, the necessary 3D underlying factors can typically not be controlled. It's very difficult for such a 2D model to disentangle the physical image formation process. However, we do know the physical image formation process, so we should actually use this in our generative model. And that's exactly the idea for our approach. Instead of having just a 2D generator, we combine a 2D generator with a 3D generator. So we sample a latent code from a random distribution. Then we have a 3D generator that generates the parameters of such primitives together with the appearance of these primitives, which is then rendered using a neural rendering algorithm that's differentiable onto the 2D image plane for each object individually, as you can see here, and then composed together into the final image. The advantage of this approach is that the 3D factors can now be controlled. And at the same time, we can learn this model in a fully unsupervised fashion from 2D images, despite we can do this only for now for very simple scenes. So the key idea here is really to do joint 3D and 2D modeling. Here is an overview of the entire model, and I'd like to walk you now through this model step by step, starting on the left side with the 3D generator. The 3D generator takes a latent code drawn from a random distribution as input and produces the foreground and the background primitives in terms of their parameters. So O1 to ON are all the foreground objects, and OBG are the parameters that describe the background. Each of these primitives is represented by a pose RT, a 3D scale SI, and the appearance parameters of that object. I will leave the exact form of these primitives open for now, and we'll come back to these primitives in the experiment section because we use different primitives. We use points and cuboids and spheres and other sorts of primitives for our experimental evaluation. Now, given these generated primitives in 3D space, we use a differentiable rendering algorithm that renders a feature map, a alpha map that defines which pixel is actually part of the object and what is background or what should be transparent, as well as a depth map for each of these objects. For the background, it only defines the feature map because we assume the background is dense in the image. We then convert these features to RGB pixels using 2D convolutions. You can see here that from this feature map, we obtain a RGB representation of the car. From this feature map, we get a RGBD representation of the car. And we also refine these very coarse alpha maps using these 2D convolutions to actually fit the shape of the car. And we also refine the depth maps. These are the variables denoted by prime here. And then we render all of these individual objects and the background using alpha composition from the furthest to the smallest depth value. Now let's have a look at the loss functions. We have 3 loss functions: an adversarial loss, a compactness loss, and a geometric loss. Let's first look at the adversarial loss. We denote the entire generative process, what is inside this box here, using g theta, indicated by this dotted arrow here. That maps from latent code C to the image I hat. We use a standard adversarial loss, which consists of a discriminator that tries to play this 2-player game, that tries to fool the generator and distinguish between images generated by the generator and real images. However, we notice that if we just have this upper part here, the model doesn't work as well because there's an ambiguity. It sometimes happens that the foreground object is actually merged into the background, because the background can well represent also the foreground object. So in order to prevent this, what we do is we also created not only a real image dataset, but a real background dataset by removing the foreground objects and just rendering the background. And we have this flag here which determines if the input to the discriminator should actually be compared to an image with foreground objects or just the background image. Now, having this real background image dataset and this flag in the discriminator now allows for distinguishing foreground and background and correctly puts all the object information into the object slots here. We also have a compactness loss that tries to minimize the area of the alpha map, that tries to minimize the size of the object, because otherwise the object is unconstrained, and again, parts of the object could be rendered as foreground that are actually part of the background. In order to do so, we simply minimize the expectation over the latent code C of the L1 norm of the alpha map to turn as many pixels as possible to black. And finally, we have a geometric consistency term that enforces 3D geometric consistency. Remember that we have these 2D convolutions, which means that after rendering, the 3D consistency might be violated because of this deformation through the 2D convolutions. So what we do here is we take a feature representation xi prime and compare it to the same feature representation after randomly transforming the object in 3D, rotating and translating the object, and warping it back according to the corresponding depth map. We always have the depth map, so we can always warp all the pixels back. So we can look at the object from multiple sides and make sure that these objects actually look consistent. And we do this for all the objects, for all the slots that we have, I1 to n, and we multiply with the alpha map to only consider pixels that are actually on the object for this loss. And we do this not only for the feature maps, but also for the depth map. We can also make sure that the geometry, not only the appearance, is actually consistent across multiple viewpoints. Okay, so let's look at some results. We used multiple datasets for our experiments. We used, on the one hand, a simple car dataset rendered without background. Then we used a car dataset with background. We used a rendered indoor datasets where we have CAD models superimposed on real background images. And we use a fruit dataset. This is a real dataset that we captured using a camera, where we put artificial food in front of random backgrounds in our lab. So here are our results. We compare to 2 baselines. First, we compare to layout to im, which is a 2D only baseline. So it has only control over 2D translation. And it also requires 2D bounding box supervision. It's a form of an autoencoder where the appearance of the content of a bounding box is encoded and then composed into an entire image and decoded back into the image. However, we observed that this baseline fails to disentangle the object identity and the pose. If we try to synthesize a layout and then move the bounding box that has synthesized the layout, the object appearance will change completely, which is fine for the discriminator, of course, because it sees only individual images. It doesn't need to be consistent. But if we want to have a controllable model, it's of course undesirable if we move the object that the identity can completely switch from blue to yellow to red to gray. We also created a baseline from our approach by removing the 3D part. What we do here is we have the generator directly predicting 2D primitives in the form of 2D bounding boxes that are directly fed into these 2D conf layers here, these little units here. And this model uses the same adversarial loss as our full 3D model. Now, compared to our full 3D model, this only provides 2D translational control. And while the identity is not entangled with the translation, it fails to, of course, disentangle rotation and translation because it doesn't know anything about rotation in 3D. So if we move this object, as you can see here, then it also changes the rotation of the object. And here are some results from our approach, our full 3D model, where we have moved objects, in this case the blue object here, in 3D space, where we have rotated it. You can see that it rotates here without being moved. Or we rotate the entire scene by rotating the camera around the scene, or here changing the elevation angle in the last row of the camera. Let's have a look at this results in form of a video. Here we can see the synthetic car dataset, some training samples from that dataset. Note that we use only images as input to our method and don't require any 2D or 3D labels. As you can see, for the baseline, the identity switches if we translate the object. Our 2D baseline changes rotation when we translate the object. Now here's the results from our full model, where you can see that the identity is maintained when translating the object or rotating the object. Here we change the camera viewpoint. And here we change the elevation of the camera. Here are some results on the flying furniture indoor dataset, where the training samples are created by superimposing 3D CAD models on random backgrounds. Again, only images are input to our model. No 2D or 3D labels. Here are some results where the camera is rotated. And here are some results finally on the fruit dataset, where you can see translation of objects. To further analyze our model, we investigated what is actually a good 3D representation. We haven't talked much about the 3D representation, the primitive-based representation that was used before. So we tried to look at different representation and see which representation actually fits best. As a baseline, we always have the vanilla gun, the 2D gun, where we also can compute an FID score, but we cannot compute these other metrics. The FID-T metric and the FID-R metric are computed by, for the 3D controllable models, rotating the object and measuring the inception distance for the rotated and translated object. And FID-I is computed by looking at each object individually. So these metrics here basically quantify how well our model disentangles the 3D underlying factors. So what we compared first is a simple point cloud, a cuboid, and a sphere representation. For the point cloud, we rendered little 2D Gaussians into the image corresponding to the points and the size corresponding to the distance of the point. And in the feature channels, we encode the feature information for encoding the appearance of the object. Here you can see also in the second column the alpha map color-coded for the different object channels and also the final image that was produced. For the cuboid primitive, we predict in 3D the coordinates, the pose, and the shape of a 3D cuboid, of a 3D bounding box, that we then render into the image, also using some smoothing. And then we have a sphere representation where we render spheres into the image, which can of course also be rotated and translated and scaled. Again, in the feature channels, we encode the appearance information. What we observe from this experiment is that all of them yield very similar FID scores. So it seems like the precise form of the 3D representation is less relevant than the general concept of joint 3D and 2D modeling. However, spheres perform slightly better as the others, as they don't suffer as much from surface discontinuities compared to the other representations. We also looked at what happens when we just use a single primitive, in this case a point-based representation, to represent the entire scene. Of course, the objects are not separatable anymore, so there's no separate control over each individual object anymore. However, the FID scores are a little bit lower even than for our object-based representation, because it's a bit easier for the model to learn only a single primitive. However, what we observed is that the number of objects now varies with respect to the viewpoint, because the model cannot distinguish different number of objects anymore. So we have, when we change, for instance, when we rotate the scene, can happen that like this red car here completely disappears. And finally, we also experimented with a standard differentiable rendering mesh-based representation where we don't have any 2D convolutions, but just use a textured mesh. So our 3D generator predicts the vertices and faces and the texture map of a mesh. And then we render that mesh to the image using differentiable rendering. However, of course, inferring a mesh using a deep neural network is not easy, which is also reflected by these numbers here, which indicate lower image fidelity, as you also can see here by the rendering on the right. Let's also look at some failure cases of our model. Well, first of all, the model works only on simplistic scenes, and a big challenge will of course be how to scale this to more realistic scenes and also to higher resolutions. But some failure cases that we observed on these simpler data sets are that in some cases multiple objects are represented by one primitive, as here when we move the banana and the orange together as a single primitive. Or the object identity may vary, as in this case where we rotate the camera by a large degree and this bench changes into a chair. We were wondering, well, I mean, it's great that we can get some factorized 3D representation of images in a completely unsupervised way, but we were not super happy by the complexity that we could handle and also by the resolution that we could output and by the quality of the models. So we're wondering, is there a better 3D representation for 3D controllable image synthesis? And indeed, there is a couple of baselines that have recently appeared, famously Hologun, that are producing images of single objects. So Hologun is a representation that uses a 3D voxelized feature representation that is then convolved by 3D convolutions and rotated into the viewpoint and then convolved by more 2D convolutions, a neural rendering step in order to yield the final image. What we observed is that Hologun leads to high image fidelity, as you can see from here, but the object identity may vary with the viewpoint due to the learnable projection. Right? So there is some 3D and some 2D convolutional layers followed after posing the 3D feature cube, which allows for changing not only the appearance, but also changing the object shape or the viewpoint. This leads to a sort of entangled representation, in particular for extreme viewpoint changes, as also evidenced by our 3D reconstruction result. What we did here is basically we generated multiple images of the same object from different viewpoints and tried to reconstruct this back using a state-of-the-art 3D reconstruction pipeline. You can see that reconstruction looks very noisy. Another representation that has recently been proposed for single image object synthesis is to directly have a 3D convolutional network that directly predicts the 3D object in terms of its colors, which are then rendered onto the image plane without any subsequent 2D convolutions that could potentially entangle the 3D factors again. And indeed, this leads to more multi-view consistent results, but because this is very difficult and can be done only at low image fidelity, or otherwise would require too much memory, the appearance that is rendered is, or the image fidelity that we obtain is typically not very high, which also reflects in the reconstruction results because it's more difficult to match features on this type of images. So what we did instead is we looked at a representation that has been recently proposed in the context of novel view synthesis, neural radiance fields, and try to build a generative model for neural radiance fields, which then become conditional neural radiance fields. You can see this here. We have a random code that we sample, and then we have this conditional radiance field G that takes this random code, a viewing direction D, and a 3D location X as input, and outputs a color value and a volume density at every 3D point in the scene, which can then be queried through a volumetric rendering, a differentiable volumetric renderer, in order to produce an image. And it turns out that these radiance fields are actually not only a useful representation for novel view synthesis, but also for generative models. So they lead to high quality reconstructions that can be queried at resolutions of 512 square pixel or even more. And when you reconstruct them using a reconstruction algorithm, you get much more consistent reconstructions. So this representation that we propose for generative model is multi-view consistent by default because we don't have any 2D convolutions. It's continuous, it can be queried at arbitrary precision, and therefore leads to high image fidelity with low memory consumption. So here is a short overview of our model. We have a generator and a discriminator, and key to making this work is our patch discriminator, which considers a dilated patch of size 32 by 32 pixel, where we randomly choose the scale and therefore the dilation factor during both for the generator and for the discriminator to enable a efficient 2D convolutional network as the discriminator. What you can see here is that the input to this generator are the latent codes CS and CA for shape and appearance, as well as the camera matrix and the extrinsics. This is the camera pose, as well as the parameters of this patch. These are the position of this patch that should be generated. We don't generate the entire image. This would be way too costly. We just generate this patch with a certain dilation factor and translation. And then for each ray on this patch, we can query the color of this radiance field by doing 3D sampling along each ray and querying the radiance field and doing volume rendering in order to obtain this patch. And then we can sample the same patch from a real image and compare these two, which is what our patch discriminator does. And this works remarkably well as a generative model. It produces not only compelling results in terms of appearance, which we were very surprised by, but also very good results in terms of depth. Note that depth is not part of the input of the model. The input of the model is only a set of RGB images, unposed RGB images. So here you can see some interpolations between different shapes and appearances and poses. So the question is, what's next? Well, of course, we want to extend this high-resolution model that can produce single objects to entire 3D scenes, as I've shown in the first part of the presentation. But then we want to also make this model work on real data. Already in 2016, we've proposed a dataset which we termed Kitty 360, which we have never actually released because the project was done with an intern, and so we never really made the dataset come out. You know, the last 10% always take 90% of the time, so it took us significant more steps in order to make this dataset ready. But now we have it ready, and we will release it this summer. It's called Kitty 360, a successor of the Kitty dataset. It has 73 kilometers of driving and 2 times for stereo, left and right, 83,000 frames. Actually, it's not slightly incorrect. We have more than 2 cameras. We have also fisheye cameras, so we have full 360-degree view. That's why it's called Kitty 360. We have a laser scanner, a push-broom laser scanner that gives a wider field of coverage for the 3D points. And we have fisheye cameras for full 3D 600-degree view. The semantic label, we have semantic labels for all 3D points and for all pixels in the images. And the label definition is consistent with cityscapes. We have 90 classes for evaluation. And we have instance labels for buildings, vehicles, pedestrians, traffic signs, basically for all instance classes. And each instance is assigned with a consistent instance ID across all frames. So everything is really consistent in 3D across this entire dataset. The way we obtain this dataset is by annotating the dataset in 3D using bounding boxes. But in contrast to Kitty, here for Kitty 360, we annotate everything using bounding boxes: the road, the sidewalk, the buildings, the trees, and the vehicles, and so on. This gives us semantic information for all these points that we then fuse in a joint 3D 2D optimization step, and also the instance information, such that they also obtain semantic information in the images. This is an approximate ground truth. It's an inferred ground truth, but it's actually quite precise. And we have this not only for semantics, we have it also for instance, and we can also give an assessment about the confidence at each individual pixel. And of course, we have the original 3D bounding boxes where this dataset was generated from. Now, what I want to show you now is a little cinematic trailer that we have created for this dataset, which I'm going to start now. Okay, so I hope this data set will become useful to the community, in particular for pose estimation, for localization, for visual odometry, for mapping, for simultaneous localization and mapping. Also, when it comes to the object level where semantics and instances are considered, but also for the task of generative modeling, as I was talking about today. I want to thank you for your attention, and I want to point you also to this little website that we've created. We have a little blog where we feature new research updates from our group, so if you're interested, I invite you to have a look. Thanks a lot.
I would like to thank the speaker, and I'm also happy to welcome Andreas Geiger to the Q&A session. I think he should be able to hear us now.
Hey, can you hear me?
Hi. Yes, we can hear you. Let me ask one question from the audience. The current state-of-the-art 3D generative models, like you presented, are able to generate simple objects or scenes with simple layouts. What do you think is the key towards making these 3D generative models handle more sophisticated scenarios? For example, the outdoor scenes such as in Kitty. Is it more on the work on the 3D scene representation, the network architecture, or is it a limitation of the dataset?
That's a really good question. It's kind of the holy grail that we are striving for. So what we've seen is, I mean, 2D generative models are really powerful in modeling parts of the image manifold, but that doesn't necessarily mean that they generate 3D consistent results, right? And so combining 3D consistency with high image fidelity is certainly not solved. And then for the question, yeah, I can't give a definite answer. It's really difficult. I think like a certain level of weak supervision has probably to be provided in order to scale these models to larger scenes, and some of this supervision is relatively easy to obtain. So I'm thinking about like sparse 3D bounding boxes or point clicks, like nothing like a dense segmentation or a dense semantic segmentation or correspondences, and combining this with all the tricks we have, like self-supervision, etc. And then also the representation side is not fully developed. I think like the answer to the question is really in all these fields, right? So some of the representations that we have, they really just work well for single objects. So you need to compose them. But if you compose them, then scaling them to hundreds or thousands of objects is hard. So I think we need to work on all of these aspects.
Okay, thanks a lot for the answer. I would have one more question. In your presentation, you mentioned that one of the challenges for these 3D generative models seems to be the differentiation between foreground objects and the background. And here you also mentioned that you're generating a separate background data set. It seems to be quite expensive and not always feasible to do so. What do you think, would using additional depth information be an alternative to overcome the foreground background separation problem? And because this can be obtained as a quite low cost with depth prediction or structure for motion.
Right. So I think this will definitely help. So having depth will certainly help. Depth doesn't directly give you a segmentation, right? So you might still need some weak form of supervision. In some cases, obtaining background information is actually not that hard. So if you think about having a car driving through a city several times a year, then the location, at least of the dynamic objects, will change. And so you can get some background information, but certainly not for all the objects. And then also for some objects like the trees, the appearance will change. And so there's all these interdependencies which make it hard to disentangle. That's why I think like some level of weak supervision will tremendously help. And then all the supervision that you can get for free, as you mentioned, like 3D reconstruction that you can get relatively cheaply through laser scanners or self-supervision, etc. Yes.
Okay, thanks a lot for the answer. There would be another question regarding the proposed Kitty 360 dataset. The question is, was the same hard and software used? I feel like it's related to the same hard and software to the original Kitty dataset. Maybe you can again point out the key differences between those two data sets.
Right. So it is the same car. So basically, I did the Kitty data set during my PhD as a side product because I kind of needed it for my research. And then we thought it's a good idea to make it more generally available, and it became successful. This was recorded, the original Kitty data set was recorded in 2010, 2011, I think. Now, this data set was recorded in 2013, so it's a little bit later. It's different data. It's not just new annotations, and it's also 2 new sensors. So in the original Kitty data set, we had only this Velodyne scanner, and the scanner has only a very limited field of view in the vertical direction. So you couldn't see, for instance, the roofs of buildings, etc. And so we added an additional push broom scanner, a very simple one, a cheap one. Actually bought it on eBay, that we put on the vehicle. So it's a simple 6 scanner, where we could, for the static objects, then also record the building rooftops. And we added these fisheye cameras to the left and to the right, which give basically a full 360-degree field of view. And we have used this already in some projects before we were able to release all of the data sets. So in one project, for instance, where we look at generative models or differentiable rendering in these outdoor-like scenes, it's important to know the environment map. So these 360-degree cameras, they can help you in localization, but they also give you great environment maps that are give you the environment lighting in order to properly relight your objects in the scene, etc. So these are basically, from the sensor side, the 2 modifications that we did. And then from the annotations, we have now all the annotations, and we have tried to be as consistent as possible with the previous semantic class definitions and the semantic class definitions of cityscapes, so that people can do cross-training and testing and look for robustness of the algorithms, etc. So we really hope that with this data set, we can go towards building full 3D city models, building generative models with as little user input as possible by having these annotations either for evaluation or using them for weak supervision.
Okay, thanks much for the other. I think the following up question is already related to your answer you gave already, but I can still ask again. So implicit 3D models seem to need very good sensor position information. Do you think current datasets, especially like e.g. Kitty 360, provide enough precision of the camera poses to use implicit models?
So the question is, the commenter here asked probably about like these implicit models like occupancy network, etc. So in terms of supervision, you need, so it's true that there's some limitations in these models in terms of requiring canonical poses, etc. But that depends on the model type that you're using, and it's not like you couldn't optimize also for the camera pose. So if you have a rough initialization of the camera pose, then it's still possible to backpropagate to the camera pose to fine-tune the camera pose. I don't think that the position or the inaccuracy in the position that we have is necessarily the major problem. Also for the new, like in particular for the new data set we have better precision. So we have improved the way we calculate. First of all, the position that we supply is fully geolocalized. So we have the exact nearly centimeter accurate position of every point in the 3D world. It can be used to combine it with information, for instance, from OpenStreetMap or other mapping services. And we have optimized the position not only to be geo-accurate, but also to be like more accurate in general by using more sensor modalities. So not only using feature-based optimization, but also using the laser scanner, including the laser scanners as observations, which we didn't do for the original Kitty dataset. So we hope that at least for the like 95% of the dataset, the accuracy of the camera pose is actually better than we had before, but we will see.
All right, thanks a lot for answering those questions. I think if there are no more questions from the audience, I am happy to thank you again for answering those questions and joining our session.
Yeah, thanks for having me. Sorry, I couldn't turn on the webcam because the connection where I'm currently is pretty low quality. So
no, thanks a lot for joining our event. It's a pleasure to have you here.
Yeah,
and with these words, I would like to also conclude the morning session. I'm also grateful to all the other speakers of the session in the morning. And I would highly recommend you to join our afternoon session, which will be starting at 4 p.m. UTC +1 time, where we would have another exciting talks from Stefan Leutenecker. We would also have a talk from Raquel Urtasun. We would also feature Cyril Stachnis, and we would have our winners of the relocalization challenge. So I'm really looking forward to see you all again, and yeah, see you later. Thanks a lot for joining.